loads, parameters, and we also say display label with the total value of the load. So in this way we will get some additional data. So not only this brown, you see we have here a force equivalent of 15 kilonewton inside one node. Inside this node, if we go to the other side of the panel, we can see a different value, which is 15. Okay, it's pretty much the same value. So it's correct. The way I tested it looks correct. We'll try to calculate the entire building. For this to have a very fast response, we will change in the mesh setup, we'll have a low refinement, so we'll get some faster results. Hit automatic, okay, mesh of size elements, okay. So I will say okay and see how much it takes. I don't want to use to waste time with the transfer of the model to the other computer. So I want to see the speed of it. If the discretion is 1 meter, we'll get faster results. Can be 10 times faster than the models with 0.5. However, the model with 0.5 will be necessary for designing the slabs and the walls. But for global analysis, 1 meter, the average size of the finite element should be enough. Also, in the meantime, while it calculates, we can discuss a bit about the following, the next topic in your list. Let me open it.
Sometimes I check the result for the placement of wall or slab, and then my computer stuck.
Okay. Well, you need a good computer for big models like this one, and you will need to close some other background applications. So SIA basically relies on the processor speed. So for calculation, it will use all the cores, but while modeling, it will only use one core. In CI17, they want to make it multi-core even in the modeling stage. So what I wanted to talk to you is regarding the other problems you would like to talk, which is the foundation or infrastructure. So while it calculates, we can have a little discussion. You sent me, but I don't know where I saved it. If I go to Facebook.
No.
So the next discussion will be mat and pile mat foundations. So the way you model the building is a bit well, it's not the way we can design the foundation. So we need two models, one where we consider the building fixed to design all the structural element or superstructure, and then assess the global behavior of the entire building. And after we finish the design on this side, we can design the foundations. So only after we finish designing the superstructure and we don't intend to do any more changes, we'll save as with a new name where we add the foundation. In order to model the foundation, we can have two options. So for this type of foundation, we can either rely everything on piles, so we transfer the loads to the piles. So the only purpose of the mat foundation is to do the transfer to the piles, and everything from capacity point of view relies on those piles. Or we can have a mixed approach where we can say that a part of the loads will go to the mat foundation and other parts will rely on the piles. So this transfer will be determined by the elastic coefficients we are going to use when we model the infrastructure of this building. But first of all, we will need to concentrate it on designing the structure. So basically, I would skip this for the second lesson.
Yeah.
You needed this, of
And,
course, because this
checklist.
it is very important for you to deliver first the foundations to obtain the permit to build. But we cannot get here until all the others are done. So basically, the normal. After we finish, I'll also check the loads you implemented in SIA. Then we'll do analysis and design and stability check of the entire building. Then we'll go to each structural elements, the beams, the columns, the shear walls. And okay, this was, I sent you the explanation. And only after we finish all this general analysis and superstructure analysis can we concentrate on the foundation, the mat and the pile mat. The piles is a bit complicated to design in Cambodia with SIA. The problem is with the pile, you will need to evaluate the capacity somehow. In Holland or Germany, they use cone penetration tests. They have a specific file which is based on the ground testing, and without that particular file format, we cannot determine the capacity of the piles. So you need to have one manual assessment of the capacity of the pile, and also we can do an assessment of the stiffness of the piles. You can either do it manually or you can use some other software. I can do a recommendation for either a pile group, so you can either use this from Geo5.
Cool.
So Geo5 will allow you to, you can ask here for a demo or whatever, and you can do this testing. So you can dimension the piles and get also the stiffness of the pile. Because once you know the capacity of the pile and you get this diagram of load settlement curve, we can establish the stiffness of the pile and the capacity. And in SIA, we will place some... yes? You have a question?
My internet is very slow.
What?
My building stand on the stone.
Yes, but you use piles, right? Or not?
The soil test result. The soil test result is the stone.
Okay, stone, but the building is very tall.
Yeah.
So there's a risk of the building to collapse generate as a rigid body. So it can just collapse on one side as it's really tall and there's small part of it buried within the ground. So we need to make this stability analysis to see if the building will collide or not. SIA will not do this automatic for you. I'll show you how you can evaluate this. We will take some forces from SIA, but we'll do also some hand calculation to make sure that the entire building will not fall, will not collapse generally just by rotating. So this type of analysis is not covered by SIA, but we will do it by hand, taking forces from SIA. So basically the moment that tries to tip the building has to be lower than the moment that withholds the building. So this is how we'll evaluate. So we'll have to make sure that the columns that are pulled by the horizontal action of the wind, let's say, won't have will have enough capacity or weight to withhold those forces. Okay, but of course, until we do that general analysis, we will have to also dimension this type of elements. So we'll see some displacements of the building, and also uh, see if these are enough, the dimensions for these are enough, and then we'll evaluate. So once we finish the concrete, we'll see if it's the stability. We'll do this manual stability check, and only then we can establish the reinforcement for each structural elements, because the stability check is not dependent on the reinforcement but rather only on the concrete. So we need to have enough weight to maintain the center of gravity within the mat, so we don't have a center of gravity outside of the mat.
Not yet finished.
Now it's
Run.
only transferring the load, so it didn't start the calculation yet. The calculation starts once you see the solver set up. So basically now it's doing it's transferring to all the nodes of the structure the wind load, and also on the shear walls placed on the sides of the building. So we'll have to wait to do this placement first. Okay, so now what I would like to check is how the building acts with this wind. So basically I need to see if it deforms accordingly, so it has a good deformed shape. For this I'll go to deformed shape, let's say of all the building. So one check should always be with self-weight, because I need to assess the self-weight in order to see if your model is correctly connected. So this is what I recommend, always check with the self-weight to see if it's a plausible deformation. So we see here the way it moves under self-weight.
Yes.
Okay, it seems correct.
Sometimes we can check the deform structure is correct or not.
Okay, so from my point of view it looks pretty good. Let's see now with the wind.
It is very, very slow.
Well, the model is quite big, this is why. So this is for wind 1 acting on per direction 0, so I think on x direction with positive CPE and CPI, which are geometric coefficients. I would say animation window. And you can see how it moves globally on wind. So it behaves quite good. You can even see some value. If I go to preview, I'll see a maximum deflection. Yes, it's you have a limit for the wind deflection on top. I think you mentioned it previously. The building height divided by 500 or something.
Yeah.
You have a limit in your code?
What about your code?
By our code, we usually check it for seismic action and we don't check a global. But let's see like this. This is okay, and the maximum was 40 millimeters, I think.
I use a 500 from ACI,
Okay, and what is the limit in ACI?
but I just take from the video of 500.
So the height of
But
the building,
no, but I don't have a reference how to calculate about this one.
so we have the building height divided by 500, which is 231 millimeters, and only from this load we get around let's say less than 40 millimeters, but this is not a factored load. We will have to check this option with combination. So this is not the final, but this is a good start. So basically the wind doesn't really affect the horizontal of the building, so there's a good
This
chance.
direction is small, but in the direction.
Okay, in that
I mean,
direction I expect something
yeah,
greater
yeah.
because of the shape. It acts only a small surface here, but on the other it's a bigger. Okay, it's still the same direction, so I'll say 90 degrees. And here we might expect
Yeah.
a bigger value as your building
Yeah.
is rectangular.
Yeah. Excuse me, can you give me a reference for the lower body placement the for the whole building?
Uh, what do you need?
A lower body placement like the high on 500. Yeah.
So this is from the 0 where we consider
Like
it fixed. Yes. So basically,
like this one.
I don't think the Eurocode.
What about Eurocode?
No, but the Eurocode doesn't have this approach. The Eurocode will have a rotation per level, which we'll do together. So this is a limit in the American standard, but it's plausible. I mean, the way we got here, it's pretty much the same. For Eurocode, we don't have a limit for the top of the building. We have a limit for each floor we will discuss. So the Eurocode won't provide you this type of ratio, but rather we will assess on each level how much the relative deflection it is according to in comparison with the capacity. So for now we did this small check, which is not 100% relevant as it's only on the pure load case. So I need to evaluate this also with combination with other loads, which can help the structure, because just loading horizontal like this is actually really conservative because we don't have the self weight or other vertical acting. So now we get the correct deformation. So the deformation is quite good. So the wind is correctly generated on your structure. Um, of course, we'll need to run the analysis on more meshed version of the building, but we'll only do this once we finish with the loads. So now if I go to loads, we see here we have a generation of the loads. So that's it. So the wind is now generated. We'll need to discuss further the other loads. So only after you finish doing all the loads can we start designing the building. You said
Yeah.
you didn't place the smart parking load, or you did as uniform load? My suggestion was to place the load as point loads, because you had that system with legs, so you need to see the reaction of each legs and place them as concentrated forces, not uniform distributed forces, because it will influence the design and the behavior of the building, but it will influence the design of the elements where we place them. So what are these? Wall 10, what does it mean?
Mean that the thickness is 100 millimeters.
For the comparting,
Uh,
the inner walls, which are
brick
not structure.
masonry.
Masonry, okay.
Yeah.
So you created separate load cases according to. Okay, so these are line. Okay, it's the cladding, floor tile. These are the finishes. -1. Soil pressure. We should do some changes here, as I changed the orientation of your. So here we'll need to check that the soil will have pressure on one side. Now there's a small observation here. It looks okay, but you can only you will load the soil on elements that don't have soil on the other side. So in this instance, for this portion, this one, you don't have soil, you have soil on both sides, so there's no loading from the soils. You understand? On the left side, there's also soil, so there's no pressure, because they, even if it's in the ground, we have pressure on both sides, so they cancel each other. So you only need pressure on this part, where you have an opening inside and people live there, and also on this side you will have. So everywhere where you have basement, you have pressure, but if you only have buried structure, there's no pressure there. You understand?
Yes.
Okay, and also you lowered all vertical elements lower than this slab, and this slab you said it's gravel. Okay, it can be one approach like this, but this is not a mat foundation by any means. So this is the way you drew. You will have local elements on soil or on rock, and then this is only a slab that sits on the ground, so that's all. This is not the foundation. So if you place this element, it means that this slab has some ground support, but mainly
Yeah.
the entire building will be connected at this
This.
area. So this is the point of connection. So this won't be a mat by any means. It will only be a slab on a plate, and we will design the foundation from here. So this is a good starting point, but okay, we can keep this as well. But you will need to cancel this, so we don't need pressure on this area. You have to finish the soil pressure up until this point. So if it's not a basement, you don't need the pressure. Pressure is only where you have open space inside and ground on the other side. So if you have ground on both sides, you don't need pressure. Okay, so
Because
yes.
my modeling for for the ground is not correct.
Well, although it's not correct, it's correct for the first stage.
Because the wall is to to, uh, to the soil.
Okay, Yes, so the only contact with the soil, the real contact, is here at this level at -3 meters. Here there's also some elastic foundation for this particular slab, but it's not that relevant. So basically it is here where we have so if we don't have any closing walls here, it means that these are buried inside the ground, right? So from here to here, this is buried in the ground, right?
Yes.
Okay, so this is what I'm
So
saying.
much less no need to to support.
Yes, your slab only will have smaller deflection if you use this surface support, so it won't deflect
Yeah.
as a structural slab. That's the only difference. But I think it's more conservative at this stage to eliminate this, and we will place them when we design the reinforcement for this particular slab. But for now, because these are really stiff, the program kind of ignores. So basically you'll see, I'll show you better like this to see the differences. I'll say just from self-weight, and then we'll do combination together. And so we'll go to results, deform structure. Okay, it's exaggerated. You see, on the slab which is on the ground, it has smaller deflection than the one that is just supported here. So that's the only difference, but everything will go to these columns which are extended 3 meters inside. So basically these supports are somehow irrelevant, but we'll keep them as they are. So it's okay to keep them, but most of the structure will go here. So all the reactions we will evaluate on that level. What other loads you need to add to your model? Are there loads that you didn't add to it? You have all the loads in the model?
What do you mean?
You need you finished placing all the loads in your model? We have other loads you need help with? Or I need to know if you need to add other loads to this model or not, if you finished adding all your loads.
No, finished.
No, what? You have them all, or? So
remaining the cladding.
But you added something. You added here on the 20 centimeter edge loads. You added something, so I see you have it. So you just, if you want to take in consideration the cladding, you have to just change here the value.
Yeah.
But it's okay. I see you have cladding. Okay. So yes. Basically, if you consider we have all the loads, we can go to generate some combinations and then evaluate how the structure behaves, what are the displacements per level according to Eurocode, and if everything is okay, we can go and do an evaluation of the stability of the global structure. But I will need a break from this, so yes. I think is it okay to continue on Wednesday? Or you need Wednesday? It? Yes, okay. Wednesday. So Wednesday, let me close this.